Yes, so good morning again to those who have just joined in, and we are about to start. So this is where we start with the next chapter, Newton's laws of motion. And meanwhile, if, as I told you, any doubts are pending in vectors, then please send them across and I will help you out with that. But at this stage, at the class level, we will move on from vectors into Newton's laws of motion. Okay. So let us begin. So Newton's laws of motion, as you know, is the fundamental aspect of mechanics, which is to do with the concept of inertia and force, okay, and was formulated way back in 16th century, etc. So the entire subject of mechanics is, though it starts from kinematics, but a lot of it is the fundamental base for it is the concept of Newton's laws and force. So let us begin by understanding the statements of Newton's laws, and from there we will continue further. So as you know, the laws itself are three in number. Okay. The first one being the law of inertia. So it's not a mathematical equation, rather it's a simple principle that gives us the understanding of the property of inertia. So the statement says that any body, or in this case we'll also talk about particle, body or particle, okay, that is at rest or at a state of uniform motion has a tendency to continue in its state unless and until acted upon by an external force. Okay, something like that. I mean, the exact words in Newton's language was somewhat more cryptic because it's from far back in history. But the effect of the statement is something like that, that any body which is either at rest or in a state of motion has a tendency to continue in its state of rest either or continue in its state of uniform motion until and unless it is acted upon by an external force. Okay, that is, so this is the property of inertia. Okay, so what this statement explains is that it is the property of inertia of a body. Okay, it is the property called inertia, okay, whereby the body tends to continue at rest or uniform motion. So let us understand this property of a body with some examples. Okay. So for example, if we take a situation where something very ordinary from everyday life, okay, on a frictionless surface or on a smooth surface like a floor. So this is a smooth or what we call frictionless surface. Okay. We have a block which is lying at rest. Which is at rest. So we know that this block will not move until or unless acted upon by some external force. something external has to come and give it a push or a pull. Only in that situation, it will have a tendency to move. Either something pushes it like this, or something pulls it like this. Yeah, Yashuvardhan, I'll give you time, don't worry. But first, let's understand this principle, then you can write it down again. So this property, it is called the inertia of rest. Okay. This tendency of the body to continue in its state of rest. That is an example of what we call the inertia of rest. Okay. Similarly, I'll give you time to note down, don't worry. First, just understand all this. Another example. Now, on the same surface, let us say that body has been acted upon by some external force for a certain amount of time. So now what is happening is it's moving with a velocity. So this is moving with a uniform velocity. So this is a block moving at uniform velocity v naught. Okay. Again on a smooth surface. Yeah, Pratinav and Yashovardhan, I will give you time to write down, don't worry. But first understand these points. Okay. So this is on a smooth surface. It's already moving with a uniform velocity v naught, and the block is of mass m. Now you can see that if we want to bring the block to rest, what has to happen? Some external force has to be applied. In this case, we want to bring it to rest. So opposite to its velocity. So you have to apply the external force like this now. Only then, by the application of this force over a certain period of time, what might happen is eventually the block might come to rest. Its velocity might become zero. If you apply the correct amount of force for the correct amount of time. Yeah, impulse in other words. Okay. So this property of the body is now called the inertia of motion, so to speak. Okay. That property or that tendency to continue in uniform motion or the tendency to oppose a change in its state of motion. It tries to oppose any change in its state of motion. In fact, we'll see over here that here the force F will have to deliver an impulse. So impulse is nothing but force multiplied by time. So that will be F into some time delta t, which will be equal to the change in its momentum. Okay. Don't worry about the definition of impulse as yet. Okay, I will explain in detail more, but this is just to explain an example. So that impulse will have to become, in this case, minus mv naught to bring it to rest. To bring the mass m to rest. Okay. Why? Because we will say impulse is equal to change in momentum. So momentum we define as mass into velocity. Impulse we define as force multiplied by time. So in this case, the impulse has to be equal to change in momentum. That is final momentum minus initial momentum. Okay. So the final momentum is 0 because we want to bring it to rest, and the initial momentum was mv. So that is why we get that impulse has to be equal to change in momentum. Okay. So impulse is nothing but force multiplied by time, and this is another form of Newton's second law, which we'll be coming to very soon. But the whole point here is that the inertia that the body possesses in this case is what we call the inertia of motion. Okay. It has a tendency to continue in its state of uniform motion until and unless acted upon by an external force, which is delivering some impulse to it in order to change that momentum. So through these two examples, you understand what we actually mean by this property of inertia. So now you can take some time and go through this and also write down in detail if you like. Okay, the first of all is the statement of the first law itself, that there is a so-called property of inertia of every body, whereby it has a tendency to continue in its state, whether that state is rest or motion. If it is motion, it has a tendency to continue at uniform motion. So uniform motion means uniform velocity. Okay. If it is at rest, it has a tendency to continue at rest until and unless something external is forcing it to change that state. So that property of a body is called its inertia. I'll explain Srikita. Impulse is to do with force. Okay. So impulse is defined on the basis of force acting over a certain amount of time. Whereas, so it is an external. Like the force is applied by an external agent. Like that, the inertia is due to an external agent. Whereas momentum is the state of motion of the body. It is mass into velocity. So that is the difference between impulse and momentum. Now later we will see that the net impulse acting on the body equals exactly to the change in momentum. Okay, so inertia, when we talk about, could be the inertia of rest, wherein a body which is at rest has the tendency to continue to rest until and unless it is acted upon by external force. Or it can be inertia of motion, wherein the body is already in motion. So to change its state of motion, whether we want to bring it to rest or we want to change its velocity or whatever, it has to be acted upon by external force. So that tendency to continue in its state of uniform motion is called the inertia of motion. Okay, Vinny. Right. So in the second example, the body is in a state of motion. It has a momentum, initial momentum of m into v naught. So where momentum is a vector quantity, because you know velocity is a vector quantity. So this velocity should be expressed as a vector. Now supposing the change that we want to bring is that we want to bring the body to rest. So in order to bring the body to rest, some external force has to be applied over a duration of time. So that is where the concept of impulse comes in. The force has to deliver an impulse over a certain amount of time delta t, over time interval delta t. And that impulse has to change its momentum from the initial value, which was mv naught, to 0. So that impulse will exactly equal to the change in momentum. So the point over here is not about the equation actually, we will come back to the equation. The point is just the concept that the body possesses this property of inertia, that it has is the initial momentum mv naught. It will have a tendency to continue with uniform momentum. This momentum should not change until and unless there is some external force which is applied on it, and therefore it's delivering some impulse. So that property of a tendency to continue in its state of motion until and unless external force acts, that is called the property of inertia of motion. No, I wish impulse is actually different than force. Impulse is force multiplied by time. Okay. So the definition of impulse becomes that it is force multiplied by time. Right? That's how its dimensions or its unit becomes the same as momentum. Whereas force has a different unit compared to momentum. Okay, so impulse delivered by a force can be in many different forms. For example, you could have a situation like this, where the body is moving along. Now this time, okay, Harpriya. Okay, no problems. Finish writing this down. Okay, so as I said, don't worry about this equation right now. Okay, we will come back to these equations. The more important thing is the property of inertia of motion. That if it is in a state of motion, it has a tendency to continue in its state of motion. To change its state of motion, we need to apply force, or that force that we are applying needs to deliver some impulse. So the whole point here is that in order to change the state of motion, force needs to act, or force needs to deliver impulse. So let's understand this with another example. So again, to bring the body to rest, the force F will have to deliver an impulse over time delta t. So this is how we define impulse. It is force multiplied by time. So F into delta t. This is that operation of multiplying a vector with a scalar. Force is a vector, time is a scalar. So force into time remains a vector quantity. The symbol of impulse is J. Capital J is the symbol that we use for impulse. So now let's take another example which I've been talking about. Now in this next example, we'll see something like, let's say this is the top view of a carom coin, which is moving with some velocity along the carom board. So in this particular example now, my diagram is such that the xy plane in which this motion is happening is actually a horizontal plane. Okay, so here xy plane is a smooth horizontal surface. Okay. So z axis is the vertical, okay, which is coming out of the plane. The axis which is coming out towards you, that is the vertical axis. Okay, so this is the initial thing. Now suppose in the path of the body there is another coin now, which is like this. So what will happen here is that when the body A, which is this disc or coin or whatever, comes in contact with this other disc, so this is initial time. Now after some time, this and this come in contact. So as they come in contact, let's say they are in contact for a very short duration of time. So A and B collide. Now during the collision, very large magnitude impact force or collision force, let's say F, acts for a very short time, which you can think of as the contact time. The bodies are in contact for a very short duration of time, delta t. Okay. So that force will act on A in which sort of direction? It will act on A on this sort of direction, because he came in this direction and hit this. So this will apply a force like this. And an equal and opposite amount of force act on B. Okay. Only now we will think of it as an impulse. So force multiplied by that very short duration of time delta. Force multiplied by that very short duration of time delta. So as a result of this, what will happen? If you see what is happening to E, you will realize from your common everyday experience that after the collision, E was coming like this, it hit something, and it will go off in this sort of direction. It will come like this and go off like this. So its direction of velocity would have changed. And the magnitude of velocity also would have changed. But so E's velocity becomes something like this. Whereas B, you will realize, was at rest. So because B was already at rest, but when E came and hit it, B will start moving. So in this diagram again, what happened is E came like this and hit a stationary object. E came like this and hit a stationary object B. So E went off like this. Its motion changed from this direction to this direction. Whereas B, which was at rest, now it will start moving like this. So B's velocity let's say become like this. So here what we can see is that for E, what is happening in terms of impulse momentum is that for E, this was the initial momentum. So this mv0 was the initial momentum. Now this has a tendency to continue like this until and unless some external force acts on it. Now this time the external force acts in such a way that it delivers an impulse which causes its momentum to not only change magnitude but also to change direction. Now this becomes the final momentum. So you can see that the direction of initial momentum and final momentum are different. The initial momentum is in this sort of direction. The final momentum is in this sort of direction. So that is why the impulse that has acted would be this. It's the change in momentum. So vector difference of this and this will become this. And this is the impulse that has acted on E, which is a large amount of force acting over a short duration of time. So so again, impulse equals to the change in momentum. But this time you can see, because the impulse has acted in a direction which was not opposite to the initial momentum. It was, so the initial momentum was in this direction, but the impulse acted like this. It didn't act like this. It didn't act opposite to it. So it also changed the direction of the final momentum. So this is equal to delta P, which is, in this particular case, the impulse acted such that it changed the direction and the magnet of momentum. So again, in this case, the body E is showing an inertia of motion type of property. That is, it has a tendency to continue in its state. And it has a tendency to continue in uniform motion. Which which is its state of initial momentum. It was mv0. It was a vector like this. Okay. Until and unless external force acts. So this time the external force applies an impulse like this on it. And so its momentum changes from this to this. So this is another example of the relationship between momentum and impulse, but we'll get more into that later. Here to understand the property of inertia itself, that the body will continue, the body will tend to continue in a state of uniform motion. That means neither it has a tendency to change its direction nor its magnitude of momentum until and unless some external force acts on it. Now the external force could act in such a way that it not only changes the magnitude but also the direction. So that means even to change the direction of motion, we need to apply some external force. Obviously, to change the magnitude of momentum, we need to apply some external force. But even to change the direction, we need to apply some external force. So that is the property again of inertia. It has a tendency to continue to move along that straight line. If we want to change its direction of motion, we have to apply some external force. So again, that is the property of inertia of motion. Okay, so hope the concept of inertia of motion is clear through these examples. So this vector triangle here is again just showing this relation that impulse is equal to change in momentum. So this is vector E. and this is vector B. We draw them from a common origin. And as you know in vector algebra, head to head is the difference. If we make the arrow from A to B, then it represents B minus. If we make the arrow from B to A, it would represent A minus. Like that. This is the final momentum, this is the initial momentum. So this is the impulse. So what we learned from these two examples is that the second and the third example is that if a body is in a state of motion and we want to change that state of motion, whether we want to change the direction or magnitude, okay, we have to apply external force. On its own, the body will have a tendency to continue in its state of uniform motion. That means it will have a tendency that neither its direction should change nor the magnitude of its velocity should change. It should just maintain a constant velocity until and unless acted upon by external force. So that property of the body becomes the inertia of motion. All right, so hope you understood this. So that brings us to Newton's second law now, which is the most important one. Yeah, Amog, you can go through the recording later if you got disconnected. So we have just continued on the property of inertia. Now we come to Newton's second law. So the second law is the one which is the most important one in the sense that all our mathematical equations are based on the second one. So it says, yeah. The second law, as you know, relates force with momentum. If mass of A is less than the mass of B, no, even then A can displace B with ऐसा नहीं है that mass कम है तो it cannot displace B. Okay, as long as there is no force to oppose the force that A is applying, so it's on a frictionless surface. Your everyday experience is that it is difficult to move a heavy mass, but that is because there is friction. So the heavier the second mass, the more the amount of friction it can experience. So we need large amount of force to displace it. But imagine they are on perfectly frictionless surface, A and B. Then it doesn't matter whether A is lesser in mass than B or greater than mass. It will displace B. Okay, so these kind of things you will understand better as we come to Newton's second law and its application. Okay, so let's come to Newton's second law statement now. So the second law statement, as you all know, is that the net force acting on a body, okay, the net external force on a body or particle equals to the rate of change of its momentum. Okay. Not for mass into acceleration. That's not the statement. The statement of the Newton's second law is to do with the rate of change of momentum. So in equation form, we write it like this, that the net external force, okay, equals to what all of you understand from calculus now is the instantaneous rate of change. That means it is dp by dt. So this is the proper mathematical form of Newton's second law, where F net is equal to the net external force. In other words, it is the vector sum of all external forces acting on the body. Okay. So before you write this down, let's just understand this. Okay. So for example, if on a body there are multiple forces acting. So there are number of forces, F1, F2, F3, like this, number of forces acting. Like this, going up to N. So if forces F1, F2, etc. up to some index N act on a given body, okay, then the net external force acting on it will get defined as the vector sum of these forces, whatever the number of forces. So adding up the forces by the principles of vector algebra, that will give us the net external force, which is the left hand side of Newton's second law. Okay, now on the right hand side, of the equation, dp by dt, this is read as the instantaneous rate of change of momentum, if we denote with the symbol p vector, with respect to time. In calculus language, what we mean by dp by dt is that it is the change in momentum over a very small fraction amount of change in time. So we apply this as a limit that delta t is tending to 0. That calculus definition of instantaneous rate of change, dy by dx is delta y by delta x for a very small delta x. So that is what we mean by this. And of course, momentum, as you know, is defined as mass into velocity. So this is the proper statement and mathematical expression of Newton's second law. You should always remember this as this. It is rate of change of momentum. Yes, it does become mass into acceleration when we apply it, but the proper statement is that it is rate of change of momentum. Okay, just note down up to here first, then we'll also discuss about the units and dimensions of both sides of the equation. No, this is Newton's second law. The conservation of momentum is a different thing. Okay, this statement is just called Newton's second law. Sometimes this is called the force law. Just like the first one is called the law of inertia, it's called the law of force, because it explains the meaning of the term net force, or it relates the net force with the momentum of the body, that it is rate of change of momentum. Okay, so this is where most of our effort in this chapter is going to go in the application of Newton's second law. Now we need to understand something very carefully here before we proceed with numerical examples. Okay. No, force equals the rate of change of moment. Force equals the rate of change of moment. So first of all, in terms of dimensions, units and dimensions of the equation. I'm not sure, you might not be familiar with the term dimensions. Just stick to units. Okay. The right hand side of the equation is the rate of change of momentum. So that is such that momentum is expressed in kilogram meters per second. So therefore, the rate of change of momentum will be expressed in kilogram meters per second divided by seconds. So the unit of the right hand side becomes kilogram meters per second square. Whereas left hand side, force. The unit for force is newtons. So that is why the relationship is that 1 Newton equals to 1 kilogram meters per second square. So this statement basically means that if the magnitude of the net force is equal to 1 Newton, okay, and suppose the mass of the body is 1 kg, then, or suppose, so this force will create a rate of change of momentum such that that magnitude of the rate of change of momentum will be equal to 1 kg meter per second per second. So every 1 second, the momentum will change by magnitude of 1 kg meter. So that is the meaning of the unit, that 1 Newton equals to 1 kilogram meter per second square. That means the momentum changes by 1 kg meter per second every 1 second if the force is equal to 1 Newton. So, Smikita, hope further this makes it clear that it's not just about proportionality, it's equal to. So when the force is equal to 1 Newton, the rate of change of momentum equals to 1 kg meter per second square. That means every 1 second, the momentum is changing by an amount of 1 kg meter per second. So the so-called SI unit of force is Newton, and the SI unit of momentum is kg meter per second. Okay, so 1 Newton equals to 1 kg meter per second or kg meter per second. Right, so that is the relationship between the units on the left hand side and right hand side of the equation. Okay, now the next point. For the equation F is equal to dp by dt, where p is mass into velocity, if the body in concern is what we call a rigid body, that is, it is not flexible or it is not of variable mass, it implies that its mass m is fixed or constant. So then it implies that the right hand side of the equation, which is rate of change of momentum, will become rate of change of mass into velocity. Now mass being a constant, it just becomes rate of change of velocity with respect to time. Just apply the principles of differentiation. So differentiation of a constant into a function becomes a constant times differentiation of the function. And you know that rate of change of velocity with respect to time is nothing but mass into acceleration. Yeah, rigid body. So therefore, the net force becomes equal to mass into acceleration. But this is the case when the mass is a constant. Okay, so we are applying this to a rigid body then, such that its shape and size and mass is not changing. So if the body in concern is a rigid body, that means what we mean by rigid body is that it has a fixed shape, size, and mass. So more importantly, the mass of the body is fixed or constant. Then the right hand side of the equation, which is rate of change of momentum, reduces to mass into acceleration. So in that case, we can say that the net force acting on the body equals to mass into acceleration. Okay, is the point clear, Dhruv, now? So this becomes the statement of Newton's second law, provided we can say with confidence that the mass of the body is constant. So this is a conditional statement, whereas F is equal to dp by dt is a universal statement. It is the proper form of Newton's second law. Rate of change of momentum definition, it applies whether or not the mass is constant. But F is equal to ma, that definition applies under the special condition that mass should be constant. Now in this chapter, we will only be dealing with rigid bodies of constant mass. But in a later situation, we will see a situation where the mass might be variable. Okay, so hope you've written down this part. On the other hand, what happens if mass is variable? For a variable mass body or system, what happens is that the rate of change of momentum will then have to be calculated by product of differentiation. You know that product rule of differentiation is this. This you must have studied in differentiation. This is the product. So we apply that over here. It becomes rate of change of mass into instantaneous velocity plus mass into rate of change of velocity, or rate of change of mass into instantaneous velocity plus instantaneous mass into acceleration. This is what the net force, which is equal to the rate of change of momentum, becomes in case mass is variable. This is for a variable mass system, where dm by dt is the rate of change of mass with respect to time. Yeah, I shall explain with some examples where the mass might be variable. But there are plenty of things in everyday life where you see that the mass of the system is changing. Like you imagine a tanker moving with water leaking out from the tank from behind. So the total mass of the tanker is changing with time. Or rocket propulsion. In a rocket propelling through space, as its engines are in burn state, they are burning and throwing out fuel at an incredible rate. The mass of the rocket is constantly changing because it's throwing out combusted fuel. So the mass of fuel in its tank is coming down very rapidly because it consumes fuel at a very high rate. That's another example of variable mass system. Or a conveyor belt in industry. So as the belt is moving, mass is constantly added to it. This mass is increasing with time. We can have both kind of situations where mass is increasing with time or where mass is decreasing with time or depleting with time. I'll explain this one. So examples of variable systems, variable mass systems. Let's just note down a few examples. Conveyor belt industry. Okay, so we have this kind of belt which is on rollers, and as the belt is moving like this, constantly mass is being added to it. Its mass and is increasing with time. That is, if mass is not being removed somewhere else. Okay? We're just assuming right now mass is being added. So as the belt is moving forward, mass is being added to it. The total mass of that belt system is increasing with time. Or you have the example of a rocket. So as the rocket is moving forward, it literally throws out burning fuel at a very high rate. So dm by dt is the rate at which mass of fuel is coming out. So many kgs per second or so many tons per liter, something like that, the unit is. Now coming back to this, this is called the product law in differentiation. The product law in differentiation. You've done differentiation, right? Basics of differentiation. Yeah. So, for example, you have a function like this that y is equal to, let's say, x square sine x, and you want to find dy by dx. So क्या हो जाएगा? It becomes differentiation of x square multiplied by sine x plus x square into differentiation of sine x. This will become 2x sine x plus x square cos x. And this is what dy by dx. So this is an application of this principle, that differentiation of the product of two functions, u into v, is the first into derivative of second plus second into derivative of first, or u v prime plus v prime v. Okay. Now, of course, you can write it in reverse order also. You can write as derivative of first into second plus first into derivative of second, but basically it means this. So that is what we have applied over here. Mass is also a function of time, velocity is also a function of time, both are changing. So it becomes differentiation of the first thing into the second plus the first function multiplied by the derivative or differentiation of the second. Okay. So that is your product rule of differentiation. Here. So just note down the couple of examples also of the variable mass system as we are writing this down. Okay, so these variable mass systems will actually become our domain of study in a different chapter. That chapter is called System of Particles and Center of Mass. That will come after work power energy. So in this chapter of Newton's laws of motion, typically we will be dealing with rigid bodies or particles. Okay. So both the case of a rigid body or a particle is one where the mass is constant. So our application of Newton's second law will just become F is equal to ma. But as per your general knowledge and as per the proper definition of Newton's second law, you will understand that F is equal to ma is a conditional statement for Newton's second law. And the condition being that mass is constant. The general proper statement of Newton's second law is not F is equal to ma. It is in fact F is equal to rate of change of momentum. This is the universal general statement of Newton's second law. Okay. Now let us see the application of the law with some examples. So let's start with something very basic. Again, we have that same situation of the frictionless surface or the smooth horizontal surface, or what we can call a smooth horizontal plane, on which there is a certain block at rest initially. So this is of mass, let's say 5 kilograms at rest initially. Now from the time t equal to 0, the moment we start our stopwatch, a constant horizontal force acts on it along the x-axis like this. So from t equal to 0 onwards, a constant horizontal force F is applied by some external agent. So might be somebody pushing it, or could be, this is a charged body and there's some electric field. So that electric field is applying a force on it, whatever. We are not concerned with who the external agent is. But the magnitude of that force is, let us say, 10 newtons. So we have to find the speed of the block at t equal to 10 seconds. T equal to 0 onwards, the force starts acting. So what is the speed of the block after 10 seconds? So this is a very simple case of application of Newton's second law applied to a rigid body here. Its mass is constant. So now when you think of that body, there are a number of forces acting on it, but the net force is very simple, because while gravity is pulling it down with what we call the weight of the object, but the table or the horizontal surface is supporting it by what we call normal reaction. So these two cancel each other. But the external force that I'm applying, which is along this direction, horizontal, that goes unchallenged because there's no friction. Okay. So what is happening is that mg and n balance each other. Okay. And the external force acting horizontally, that becomes the net force. That becomes the net force because there's nothing to challenge it. So from that we realize that on this, whatever external force we are applying, which is of how much, 10 newtons magnitude, that creates a linear acceleration, which we can now find out. So F will become equal to, because that's the net external force, mass into magnitude of acceleration. So 10 newtons will become mass, which is 5 kilograms into acceleration. So the acceleration will become 2 meters per second square. And of course, here that will be a uniform acceleration. So because the force we are applying is constant, therefore this acceleration that we are getting of 2 meters per second square along the x-axis, this is a uniform acceleration. And initial velocity was 0, but it starts from rest. So therefore we can say that the velocity after time is at along x-axis. So therefore at t equal to, what was it, 10 seconds? Yeah, at t equal to 10 seconds, velocity will become 20 meters per second. So under the action of this force, you will see that this body which was at rest at t equal to 0, it now at a time of 10 seconds, its instantaneous velocity has become 20 meters per second. All this happening why? Because that force that we are applying on it is maintaining a constant acceleration of 2 meters per second. It's maintaining that uniform acceleration of 2 meters per second. This is what all this is. Okay, so this is like the most basic example of the application of Newton's second law. Just make note of this. Yes, the normal reaction force is applied by the ground. That's correct. Yes, but the thing is, the normal reaction will not on its own be greater than mg. Not unless if it's on the floor of a lift and the lift is accelerating upwards or something like that. If it's on a stationary horizontal surface, then the normal reaction will just balance the weight. Yeah. So that assumption is because the floor is at rest now. It's on a stationary horizontal surface. But suppose if it was on a moving surface, like the floor of a lift which is accelerating upwards, then yes, then what you're saying would apply. The normal reaction would exceed the weight. Or for that matter, if it's on the floor of a lift which is going down with some acceleration, then you will see that the weight actually exceeds the normal reaction. Okay, so we just used Newton's second law, F is equal to ma, applied to a body of constant mass to find the acceleration. And we know that because the force is constant in time, so is the acceleration. And then we just use kinematics. That uniform acceleration means velocity after time t becomes acceleration into time, because the body started from rest. Now let's look at another example. Now this time we will look at more than one external force acting on the body. So first of all, let us say that we are dealing with a sort of three-dimensional body. I mean, I'm making a three-dimensional diagram here. So let's say this is some kind of cuboidal box that I have. Okay, now this is lying on a surface like this, on a smooth horizontal surface. So this is so gravity would be a vector which is pointing into the surface. This is your acceleration due to gravity's direction would be like this. This is your vertically downward direction. So again, let us say this is a block of mass m. So let's say 2 kg is initially at rest on the smooth horizontal surface. Now what happens is that we have, let us say, two forces which act on it like this. F1 and F2. So let's say two people are pulling the two edges or the two corners like this. Now from t equal to 0 onwards, two external forces F1 and F2 act on it such that F1 and F2 are in the horizontal plane at an angle of, they are at an angle of 120 degrees with respect to each other. Okay. And magnitude of F1 is equal to magnitude of F2 equals to 5 newtons. So find the acceleration of the body. Now to help us understand this better, we also given the top view. The top view, that is view from above, is like this. That if this is the ceiling of that block, this is the horizontal surface on which it is lying. So here gravity is into the plane in this diagram. Gravity is a vector that is going straight into the plane. So in this diagram, the forces are drawn like this. F1 and F2 are in the horizontal plane both of same magnitude, but suppose sorry, those angles will not be 120. Just a minute. So these angles are 150 degrees each. Okay, and both are of magnitude given to us in the question. Okay, just try this out now. So what you have to do in the problem is apply Newton's second law, that the net external force is equal to mass into acceleration. So the forces are 5 newtons each. The angle between F1 and F2 is 120 beta. The angle I've shown in the diagram below, that one will be 150. You'll understand when you make the vector diagram. Yes, Chinmay, that's correct. Okay, so the more important diagram is the one below. Just pay attention to this diagram here. So in this, both these forces are 5 newtons in magnitude and the mass is 2 kilograms. So now you have to apply this equation, that the net external force will become mass into acceleration. So this net external force will be what? It will be the vector sum of F1 and F2. You just apply that. So from that you find out how much the acceleration is. So it's just a matter of vector addition, nothing else. So just do the vector addition correctly, okay, and you will get the answer. Yeah, people, so you should be getting the acceleration as 2.5 meters per second square. Okay. Yes, 2.5 is the correct answer. So it's very simple. See, one is you can just understand this by algebra. Given that magnitude of F1 is equal to magnitude of F2 is equal to 5 newtons. Okay. And the angle between them is 120 degrees. Okay. And we can see that again, mg and normal reaction balance each other. Okay. They are vertical forces. Okay. And F1 and F2 are horizontal forces. They are in the horizontal plane. Okay. So therefore, the net force will be the vector sum of F1 and M2. Because in all there are 4 forces, but out of the 4, normal reaction and mg are 2 vertical forces which are balancing each other. Okay. So the magnitude of the net force will become magnitude of F1 plus F2. So that over here will just become square root of 5 square plus 5 square plus 2 into 5 square cos 120. So you know that that will become 5 newtons. So if the magnitude of the net force is 5 newtons, it means that the magnitude of the acceleration is the magnitude of that net force divided by mass. Or you can just say that E is equal to F net by M. So the acceleration here will have a magnitude of 5 newtons divided by 2 kgs. So that will become meters per second. But you can also better understand this in the diagram. So for example, even if I had not given you the angle theta equal to 120 separately, but I had just given you the diagram, even then from the diagram you should have been able to deduce कि वो दोनों angles 150 थे, that means net force कितना हो जाएगा, be like this, because see according to the diagram these two forces are both acting at an angle of 150 and 150 to this line which is symmetric, and they are both 5 newtons in magnitude. So now from this diagram we want to find out what is F1 plus F2. So you have to understand, we have to extend this like this to understand what this angle is. What this angle is. Okay. So for that you will understand that if we draw those two vectors like this now from a common point, we draw the two vectors like this. So this is also 5 newtons. This is also 5 newtons. So this angle theta, you want to verify that it should be 120. So now if we just complete a triangle like this, you see that this is a isosceles triangle. Okay. So in this triangle, this angle should be equal to this angle. Suppose it's alpha. Okay. And you can see indirectly this angle is given to us because this angle was given to us as 150. Okay. And similarly, this angle here was given to us as 150. So you can see that theta is 180 minus 2 alpha, and alpha is 180 minus 150 on 30. So that means theta is 180 minus 2 times 30 degrees on 150. So that is the angle between the two forces. Okay, now you can see that if you want to do this geometrically also, you can do the addition of the two forces geometrically. So F1, F2. Okay, so when you complete the parallelogram, it becomes a rhombus. And this angle is 120. This side is equal to this side, equal to 5 newtons each. So use the property of the rhombus, that this diagonal will bisect this. So this will be F net, which is the vector sum of F1 plus F2. And this diagonal will bisect this angle. So this angle and this angle will be 60 degrees each. So the magnitude of F net will become 2 times 5 cos 60. So 2 into 5 into half. So it will be 5 newtons. So the net force will have a magnitude of 5 newtons, and the net force will act along the angular bisector of F1 and F2. Okay. So coming back to that block now. So now we also know the direction in which the net force is acting. So on that block, if the two individual forces were acting symmetrically on the corners like this, so that means the net force, angular bisector ना बेटा, so you can see ये दोनों force अगर ऐसे act कर रहे हैं ना, this angle is 60, this angle is 60. Okay, so their cos components are adding and their sine components are cancelling. So that's why if they have the same magnitude, so magnitude of F1 is equal to magnitude of F2 equal to F. So F net will just become 2F cos 60, because you can see that the sine components will cancel. So there's no net force along this axis, and the cos components will add. So यहाँ पे net force will become along this angular bisector. So the acceleration will also be along the angular bisector. This will be there. So that will be such that this angle is 60. This angle is 60. Okay. So the acceleration will be 5 by 2 meters per second square, and that will also be along the bisector. So not only we have information about the magnitude of the acceleration, but also about the direction using vector algebra. So this is where vector algebra becomes the backbone of Newton's laws application, because always mostly you're doing vector addition of the forces. Unless you have a very easy case where all the forces are acting parallelly. Generally speaking, the forces will be acting at some kind of angle. So you're always dealing with this vector addition. Okay, so hope this example is clear to all of you people. I mean, we've done so much of vector algebra recently that these kind of examples should not create too much problem. Just working out the geometry. Okay. Yeah, use just a second. If the forces acted parallelly, then the acceleration would have become 10 divided by 5, ना? Or 10 divided by 2, 5 meters per second square. अगर दोनों force यहाँ पे ऐसे act करते हैं, if they were acting like this, then in this case the net force would have a magnitude of F1 plus F2 because the angle between them is 0. So then that would have become 10 newtons. So then the acceleration would have become 10 by 5 or whatever, 10 by 2, 5 meters. But here it's not like this. Now, because they are acting like this, it's not this, it's this case. Right, Ayush, hope this is clear. Okay, now let's look at a different type of problem. One where we will have to apply the definition of Newton's second law rather than do vector addition of forces and things like that. Now, next example, a particle of mass 2 kg moves on the xy plane such that its instantaneous velocity v is given by this equation. It is, let's say, 5t plus 3t square I cap plus 2t square minus 6t j cap. Okay, where v is in meters per second and t is in seconds in the equation. So first of all, express its momentum as a function of time. And secondly, find the net force F acting on it at the instant t equal to 2 seconds and the magnitude of that net force. Okay. So this is not like a traditional Newton's laws question where we are given the force vectors and we have to do the vector addition. Rather, this is more to do with the definition of Newton's second law, that net force is equal to rate of change of momentum. That is the concept we'll apply over here. Or net force is equal to mass into acceleration because we are talking about a particle, so it has a fixed mass of 2 kgs. So this is more about your application of differentiation concept, how you will apply differentiation over here. So just try this out, people. So see, for momentum, just use the definition. It is mass into velocity. So the mass here is 2 kgs and the velocity is that expression given to us, 5t plus 3t square I cap plus so it is becoming 10t plus 6t square is the x component of momentum and 4t square minus 12t is becoming the y component of momentum. Okay. So this is the momentum in kilogram meters per second because the velocity was in meters per second. So that's the first part. Now second part kaise aayega? That is where Newton's second law comes in. Okay. For the second part, the net force acting on it at any point of time is rate of change of momentum. So we'll have to differentiate this whole expression with respect to time. So just because it's a vector, there's nothing different about it. Okay, you will just apply the normal principles of differentiation, where you understand that I cap and j cap are just two constants because they are unit vectors, so they're along fixed directions. So both the vectors I cap and j cap are fixed quantities in both magnitude and direction. So when you apply the differentiation, now pay attention to these steps closely. Okay. So hope up to this step is clear to all of you. Momentum and then net force is equal to rate of change of momentum. Right. So up to this step is clear. Right. So no doubts up to here. Now see, differentiation jab use karenge, just bring this operator inside. So this will become, the net force will become rate of change of this bracket 10t plus 6t square into I cap plus d by dt of this thing 4t square minus 12t into g. This we are just applying the distributive property of differentiation. The distributive property that differentiation of the sum of two functions, it becomes differentiation of the first function plus differentiation of the second function. This is the distributive property of differentiation. So that is what we are applying over here. But along with that, there's also I cap and j cap, and they are just constants. Okay, so that's why it is applied this. Very good. Ask me, that is correct. Okay, so next thing, take the differentiation inside. Okay. So just like d by dx of 10x would have been 10, so d by dt of 10t will become how much? It will become 10, and 6t square का कितना हो जाएगा? 12t. So this whole thing into I cap plus differentiation of 4t square, which will become 8t minus differentiation of 12t, which is minus 12. So this becomes our expression of force as a function of time. So we can say over here that the force has an x component of 10 plus 12t, and the force has a y component of this function. So we can see that this is a variable force. This is not a constant force. Okay. So now we can see that we want to find the force at t equal to 2 seconds. What is the net external force at t equal to 10 seconds? So 2 seconds. So just substitute t as 2 here. So it will become 10 plus 24 I cap plus 16 minus 12 j cap, or it will become 34 I cap plus 4 j cap in newtons. Yeah, function of time beta. That means it is expressed in terms of the variable of time. Like when we write y is a function of x, that means x is the independent variable. X and y is the dependent variable. Y. So like that, if I say, for example, that I'm finding momentum as a function of time, only it's a vector function. Okay. So this is momentum v. It is the dependent variable. It depends on what? The independent variable of time. It is a function of time t, where time t becomes the independent variable. Okay. So there's some relation between the linear momentum and the time t, such that that relation defines the dependence of linear momentum on the independent value of time. Okay, so that is what we've done above. We've expressed this equation. You can see we've expressed the left hand side as the dependent variable of momentum in terms of the independent variable of time on the right hand side. You understood, Nikita, how we are using the term function of over here. It's the same meaning that we have function of in maths or in the calculus branch. Okay, this is called a single variable function. The value of momentum depends on the single variable, which is time. It does not depend on anything else. So this is becoming the instantaneous force at the instant of seconds. So the force at 2 seconds is 34 I cap plus 4 j. So its magnitude will become square root of 34 square plus 4 square, which I'm not attempting to calculate. It's too much for me. Okay, beta. So this is just about the application of differentiation, nothing else. Momentum we found out as a function of time. So now we have to just apply differentiation to find the instantaneous rate of change of momentum to find the force. Okay. This is not the common type of problem we do in Newton's laws. The common type of problem is more where the forces are given to us as vectors and we have to do vector addition. But still, you should know how to do this also, because this is the definition of Newton's second law. Very good. Well done, Vinith. Brave of you to calculate. Yeah, so you can take 2 common here and become square root of 17 square plus 2 square. Very good. Enough. All right. Now, so this is about Newton's second law, a couple of examples that we saw. So we'll more or less conclude here. Next time we'll see more about application of Newton's second law. But before we leave, coming back to Newton's laws of motion, let's just note down the third statement. So that is the action-reaction principle. It states that every action has an equal and opposite reaction. So we should understand this statement a little bit better actually. What this means is that this implies that if two bodies, let's say A and B, are interacting. Now I'll explain what we mean by interacting also. Such that A applies a force on B, which we denote with the force on B because of A. So we'll write it as B comma A. Then B must apply an equal and opposite force on A, which will denote by the vector F A comma B, because this is the force on A because of B. Now, according to the statement, these two forces should be equal and opposite. So the force on B because of A must be equal and opposite to the force on A because of B. Okay. So this is the force on B applied by A, and that is equal and opposite to the force on A applied by B. So you can think of this like the action, then this is the reaction, or vice versa. If we say this one is the action, then that one becomes the reaction. But importantly, they have to be same in magnitude but opposite in direction. Okay. So that is the meaning of Newton's third law. Just a minute, I'll minimize this and you can write down this statement. And I'll also give you an example of what we mean by two bodies interacting with each other. But first, write down this statement. So this mathematical equation is the proper interpretation of this statement, that every action has an equal and opposite reaction. It means that if I am applying a force on somebody else, that somebody else will apply an equal and opposite force on me. Okay. So this is the law out of the three that we have most experienced with over experimenting over the years, especially in our childhood. When we do those kind of experiments where if you hit somebody, slap somebody, box somebody, punch somebody, whatever, then your hand or foot or whatever you used for punching, kicking, boxing, whatever, experiences an equal and opposite force. So hitting somebody or something is an equally painful experience for you as it is for that person. But here, of course, it is in a wider context. Okay. So when we're talking about interacting bodies, this could be, interaction could be, for example, it could be like that case we were talking about earlier, that the body A comes and collides with another body B. So during the interaction, what is happening is, this and this are experiencing equal and opposite forces. This is the force on A because of B. This is equal and opposite to the force on B because of B. So they will have this relationship. Okay. Or for example, we could have a situation where they are not coming in contact, but they are still interacting. So for example, A could be a charged particle and B could be another charged particle. So what will happen is they will experience repulsion such that as vectors, the force of repulsion that A experiences because of B will be exactly equal and opposite to the force of repulsion that B experiences because of B. So this pair of forces will have this behavior. This pair of forces. Okay. So this is an example of collision forces. That is the interaction. This is an example of interaction via what is called electrostatic forces or electrostatic repulsion, to be more precise, because they are like charges. So whatever the nature of the force of interaction be, but the principle will always apply that yes, Rakshit, that is only too true. We get the opposite reaction on our face also. Yes. Okay, so whatever the nature of interaction, whether it is mechanical forces of collision or it is electrostatic forces, or we'll see later gravitational forces, okay, they always follow the principle of action-reaction. No, again, Ayush, that's a good question. I usually ask the question that is it necessary that mass of the interacting body should remain constant if we are applying the action-reaction principle? The answer to that is no, it's not necessary. It's a general principle. Even in variable mass system, the action-reaction principle will apply, that every action has an equal and opposite reaction. So for example, if there's a tanker moving where water is coming out of it, so it's a system which has variable mass and something hits the tanker. So a variable mass system is interacting with something else via collision force. So even there, the action-reaction principle will apply in the same way. Even though the mass of the tanker is not constant, but the action-reaction principle will apply exactly in the same manner. Okay, people. So that brings us to a conclusion of the first lecture. So I will send you an assignment along with the notes and everything. And also, I have sent you the theory notes of the module earlier, but now I will send the full, formatted version of the module. So I will also send you some specific reading assignment from the module, because in this chapter, initially at least, the reading part will also be equally important. And then as we get more familiar with the concepts, then it will be more or less only numerical problems. But initially, the theory reading part is also going to be important. So in fact, best will be if you can get hold of a copy of René Descartes, that other book which I had recommended. So that will involve some extra time and energy in effort from your side on reading some extra things, but it will definitely benefit your overall physics. Okay. So I will send you some passages to read from René Descartes as well as from the module, apart from a basic assignment. So that's it for today's lecture, guys. All the best. In the last lecture, I have sent you some names of reference books, Pratina. So you can just see it in that whiteboard. If you can't find it, just let me know. I'll message it to you. Okay, people. Bye then. Okay, all the best.